This is Surveying 1, Lecture 16, and in this lecture we will cover the first part of electronic distance measurement. Now, we didn't touch on this subject when we talked about distance measurement using tapes, but now that we have covered some of the angle measurement topics, and because in this class we use the total station, which combines the angle measurement device with the distance measurement device, it's now time to talk about electronic distance measurement because that is the technology used in a total station. Now, the electronic distance meter or electronic distance measurement works because the speed of light was determined through experiments of physicists just quite recently in terms of scientific progress in the 1940s and 1950s. There was a Swedish experimenter who designed some pretty elaborate apparatus where they had a very carefully measured distance and developed some apparatus to develop from that the speed of light. They were basically measuring how long it took the light to get from one place to another. And as you might imagine, because the speed of light is so fast, they had to set up a fairly long baseline that surveyors were actually involved in measuring quite carefully. But once the speed of light was known, it could then be turned around and used to measure distance. However, the equipment used in measuring the speed of light was not designed to be portable, and the addition of quite a bit of electronics development that occurred during World War II and the 2 or 3 decades following it is what eventually made a relatively compact electronic distance meter possible. The first electronic distance meters were actually quite large when you included the fact that they consumed a lot of power and so needed a huge bank of automobile batteries or a generator. Pretty much required the back of 2 half-ton pickup trucks to move around. EDM in general makes surveying easier. So some of the obvious things that you have already encountered from using steel tapes is that if you have difficult terrain, if it's very steep or very rocky, or you have lots of ups and downs, you can often measure quite easily over all of this with an electronic distance meter. If your line of measurement takes you through a swamp or other kinds of water like a pond or a river, again, the electronic distance meter allows you to measure over that obstacle that makes being in the actual line being measured difficult, if not impossible. Similarly, when you're working in underbrush or dense forest where there's no underbrush but lots of tree trunks, you can have issues with the line along which you want to measure being obstructed. And the electronic distance meter, together with the theodolite measuring angles, allows you to circumvent them, and we'll talk about them at the very end of this section, probably at the end of the next lecture. And things like traffic. So when you wanted to measure across a highway, this was rather dangerous for the people making the measurement and sometimes downright impossible. Electronic distance meters can, because they project a beam of light, can be projected across the highway and essentially measurements made whenever there are gaps in the traffic. And these gaps don't have to be very large. The electronic distance meter simply understands when the distance is obstructed and when it is not. And finally, things like hostile landowners. Sometimes, as a surveyor, you are required to make measurements where someone doesn't want you in a particular place. And sometimes, very often perhaps, but sometimes you are then able to make indirect measurements somewhat similar to what I talked about, we'll be discussing at the end of this 2-part series on electronic distance measurement to make those measurements. Now, easier measurement of distance also has its downside. You get lax, you simply think all you have to do is push a button and you start to forget about some of the things that maybe you should be paying attention to. So one of the things that you need to worry about is, when is the EDM making a mistake? Now that may sound like an unusual thing. I'm talking about the actual machine or the machinery that's used, the equipment that's used, and not the person. An EDM can sometimes give you a false measurement, just as many other types of surveying technology. So the surveyor has to be acutely aware of the processors that he or she is using to make the measurements and figure out ways to eliminate the possibility of a mistake being generated by the EDM. On the other hand, the surveyor can make all kinds of mistakes with an EDM, because just as with computers, this was a joke that was often made with computers, the problem with computers, people used to say, is that now we can make mistakes faster and make bigger ones than we could when we made calculations manually. So it's the same kind of thing with an electronic distance meter. It's sometimes easy to make the process seem so simple that you're less fastidious, you're less careful, and therefore introduce more mistakes into the process. Some of the most common mistakes that are made with electronic distance meters will be described further in these two lectures, but a couple of obvious ones that you should be able to understand even at this point is, are you measuring to the correct point? And also, are you measuring from the correct point? But a lot of it has to do with not following correct procedures. A big occupational hazard, it seems like, in surveying is that there is an attitude of, I'll figure out how this machine works, rather than learning the proper way. And as soon as you get a result, you assume that it's working properly. So it's a really great idea to actually read the instruction manual with instrumentation that you have never seen before, because there are often fine points that come up that you may not be able to detect simply from pressing buttons and figuring out whether it is generating what seems to be the correct result. And finally, the other downside is simply ignoring all the various sources of errors that we will talk about in this two-lecture series, and some of the mistakes that are possible to make. So there are definite downsides, and it does require more careful, thoughtful consideration. People often say, I would rather measure with an EDM than a steel tape. The problem with that is that people don't think about all the things that can possibly go wrong, and it's amazing how many times we have EDM measurements that are made that are quite inferior to what that same person or that same team would have made had they used a steel tape, even if they didn't know the correct steel taping techniques, because sometimes the mistakes they commit with EDMs are so huge. There's also a little matter I want to talk about which has to do with servicing EDMs. There are many parts on some surveying instruments that surveyors can fix themselves. Pretty much in an electronic distance meter, there's not a whole lot you can fix. So if the thing isn't working properly, pretty much all you can do is send it to a qualified repair shop so that they can make the proper tests and then make the proper adjustments. There's a lot about physics and electronics that needs to be understood to properly service an EDM, and for the most part, most surveyors do not have that understanding. And so the advice I'm giving you here is read the manual, do what the manual says you can do, but don't do things that the manual does not mention, because more than likely you are probably either damaging the instrument or causing it to give you erratic or inaccurate results. So we'll go through some EDM terms and science. We'll kind of jump around here. So let me start by mentioning that EDM sometimes stands for electronic distance meter and sometimes for electronic distance measurement. So we kind of use it in both ways. And the principle basically depends on the signal being emitted from the instrument going to the other end of the line, which is then reflected usually by a retroprism. I say usually because I'll talk about some exceptions to those rules. So in general, we say that twice the distance is being measured. So the EDM always has some kind of electromagnetic radiation that is sent out, it comes back, and so the radiation is actually traversing the distance twice. So we're always measuring twice the distance and then taking half of that for our result. So here are some of the EDM components that I'm showing here in this slide. You essentially have what's called the measuring unit, the EDM, or the transmitter. It sends out a light wave, and I probably should say electromagnetic radiation, because it could be microwaves, and we'll talk about that a little bit more. And generally there's a reflector, something that reflects the light and sends it back to the EDM so that it can then make a calculation as to what that distance is. When we use something called microwaves, which are radio in the radio spectrum of the electromagnetic spectrum, then you essentially have another transceiver just like the one on the left side that actually receives the signal, turns it around, and rebroadcasts it through its antenna. So the carrier is the visible light or the infrared light that is used to carry the signal over to the retroreflector. When it's microwave, as I said, it's also then received by a transceiver at the other end, which rebroadcasts the signal. I mention microwave because most literature will talk about microwave, and there are few still microwave instruments in use, but to my knowledge there's none that are in production. So you should be aware that microwaves have been used. In fact, some of the very first EDMs, not the very first one, but some of the early EDMs are all microwave based. And so we sometimes say, if we're using microwave, what is called the reflector is active, meaning we actually have electronics that are receiving the signal and retransmitting it to be the equivalent of a reflector. On the other hand, if it's visible or infrared light, we say the reflector is passive because it's acting a little bit like a mirror does, except that a mirror works a little bit differently, and we'll talk about that more when we discuss the retroreflectors or prisms. Now, for very short distances, you need to realize that things like reflective tape or tail light style reflectors or highway reflectors can also work to reflect the optical signal, the visible light or the infrared light. And that's because inside those reflectors are things that look very much like a retroreflector that a surveyor would use. And inside the reflective tape, if you look at it closely, are glass beads that are small spheres. And it turns out a small sphere acts very much like a retroreflector. So let's talk about the retroreflector, and most often it's called a retroprism. Now it's very common for surveyors in practice to call them mirrors, but there's a big difference between a mirror and a retroreflector. So this is a cross-section of a prism, and basically if we take a cube of glass and cut it at one of the corners and you turn it on edge, you have this triangular shape. And what you are essentially doing is sending your light from the EDM into that face where you made the cut. And so what happens is you have three faces that are at right angles to each other. And what happens is that the light comes in, reflects, and comes back out. So even, and I'm going to just draw this in here for now, and I'm going to take it out in a second, but even if the light comes in at an angle like this, what now happens is the light reflects here, goes over here, and comes back out parallel to the direction it came in, because that's kind of the ideal situation. So let me remove this sketch here. and continue with what I was discussing. On the other hand, if we had a mirror, an actual flat mirror like you have on your bathroom cabinet at home, that mirror would have to be exactly perpendicular to the line of sight to reflect the light back. If there's even a slight deviation, your reflected light would go off and never come back to the EDM. So a real mirror is useless, and that's why I tell people don't call it a mirror, because it isn't a mirror. It's a retroreflector or a retroprism, and sometimes they're referred to as corner cubes, and that's why I drew this particular illustration. The interesting thing is, even if that aiming of the reflector is not perfect, this arrangement causes the light to go back in the direction that it came from. And the interesting thing is that the light is actually traveling a distance here. I'm going to call these distances A, B, and C. And it turns out that even if you have a tilted retroprism, A, B, and C will be different lengths, and certainly A and C will not be equal to each other, but certainly the sum of A, B, and C will still continue to be the same, meaning the light traveling through the prism, which must be accounted for, is still constant in this setup. Now, when you try to make measurements with an EDM, one of the problems that sometimes happens is you cannot make a measurement because the light is traveling long enough distance that there's a drop off in the intensity of the light so that the electronic distance meter is not able to receive the reflected light. So one way that's handled is by using more prisms, and it's very common sometimes, instead of using a single prism, to maybe have a triple prism, and there's even more arrangements where people use 9 and 12 and 15 prisms for exceptionally long distances. These days, those exceptional combinations are not used very much, because for exceptionally long distances we now use GPS or GNSS to make the measurements. The other way to get a range increase is to make sure that the carrier wave is actually a laser, because the laser projects a more tightly focused beam, meaning that there's less dissipation of the signal, and therefore more of that energy comes back to the electronic distance meter. There are two kinds of EDMs, and I'm going to call them electro-optical EDMs. You should be aware of that term. That's to distinguish them from the microwave system. So the microwave system is not electro-optical. It's actually microwave or radio based. Electro-optical, on the other hand, are projecting light. Sometimes it's visible, sometimes it's invisible. The invisible is the infrared. The visible is more than often not a red laser, although I have seen green lasers used occasionally. We have two types. One is called a phase shift EDM, the other is called a time of flight EDM. Now, many people think that all EDMs out there in existence since the beginning of time have been time of flight EDMs. It turns out that the technology is such that time of flight EDMs have only come about fairly recently, that most of the EDMs that have been manufactured since the beginning of time have actually been phase shift EDMs. Phase shift EDMs have to use reflectors of one kind or another. You might be able to get away with a tail light style reflector or reflective tape. It's an extremely short distance, but for most practical surveying distances, you pretty much have to use a retroprism. However, with time of flight reflectors, turns out you're packing more energy into the individual pulses of light, so you can use it in reflectorless mode so that it is still returning enough light to the transmitter. However, even with these kinds of EDMs, if you're measuring a long distance or it's a little bit hazy so that the atmosphere is attenuating or reducing the strength of the signal, you'll often find that using the reflector will make that measurement possible. So with the phase shift EDM, this is to simply illustrate what happens here. When the phase, they essentially think of it as the light being turned on and off very fast. And when I say very fast, I'm talking about speeds in the hundreds of thousands or millions or even sometimes tens of millions times a second. So if you can imagine the light turning on and off, you essentially are creating a sine wave of intensity of the light. And so by changing the measurement, it's possible then to determine what's called the phase shift on the return signal. So this signal here, let's say, is the outgoing signal. So if I trace this, here's the outgoing signal. Gets to the center of the EDM, and then when it comes back out, it's shifted. And that's what this looks like. And because of this shift, we can measure that very accurately inside the EDM. Even though that shift is shown here as distance d, on the right side, it's actually measured inside the electronic distance meter. And so this is the incoming, what I traced in blue. And now we have the issue of how to figure out the distance, because we know how much the phase shifted, and then we have basically a certain number of wavelengths multiplied by that known lambda, which is, if we know how fast we're turning the light, if you will, on and off, we know exactly how long each pulse of light is every time it reaches maximum intensity. So it's n lambda plus the distance d, and then we divide the whole thing by 2 to get the distance. This is not an incredibly important process to understand mathematically to the nth degree, but I want you to understand that phase shift EDMs do exist, and this is how they work. And so the way this is solved is we use different frequencies so that we have different lambdas, and we do what's called a simultaneous solution of the equations. And so I already have this on the previous slide, but there it is. N is the number of full wavelengths times lambda, which is the wavelength, plus the phase shift. That's the total distance out and back, and then we divide it by 2 to get the actual distance between the reflector and the EDM. In the time of flight instrumentation, what we do is we send a pulse out, it hits the reflector, it comes back, and we're measuring time very accurately. This is not as easy as it sounds, because when we have an EDM and it sends out a pulse, we don't know the exact shape of the pulse. And then it strikes this surface, whether it's a retroreflector or say a wall or a tree or whatever it is that you're surveying. The pulses don't come back looking the same way, so they get intensely distorted, and it's hard to know where the beginning and end of these pulses are. And so a lot of the science with time of flight EDMs, number one, is being able to measure time very accurately, because we're talking about picoseconds sometimes, billionths of a second in the time of flight. But the other significant thing is that they have to have some very sophisticated, what's called signal processing, to figure out when to match up the pulses, to figure out how long the pulse has been in transit, to then figure out the distance, and the distance is simply calculated using this equation. I don't expect you to understand and use these equations mathematically. I want you to understand the concepts that fit into this process. So let's talk about errors with electronic distance meters. So they come from different areas, and we'll have a more categorical kind of listing of some of the errors that happen, but let's just talk about some general things. The speed of light, as I mentioned at the beginning of this lecture, was determined, but it was calculated for a vacuum. Now, when surveyors use electronic distance meters, they really need to adjust for the fact that the speed of light through the atmosphere is affected by the temperature of the atmosphere, the barometric pressure, and the relative humidity. Now, it turns out that the relative humidity is about half a part per million for most electro-optical distance meters. So typically, unless you're doing a geodetic quality EDM measurement, it's not necessary to measure relative humidity. But you do have to make corrections for barometric pressure and temperature. The good thing today, compared to when EDM were first introduced, is that most instruments have a way to directly input what we call a ppm correction, where you enter the temperature and pressure of the atmosphere from your measurements or your estimation, and the instrument then calculates what the ppm adjustment needs to be and then applies it. Now, some of the ppm mistakes that occur with most surveyors is that they tend to assume that the correction is not significant or that it can be zero. That isn't that common that it's actually zero, which means that you need to understand how much ppm correction you're ignoring before you can understand that it's not significant. Now, on extremely short distances, it may be okay because the impact of a few parts per million may not be much. But you still need to have a handle on how large these corrections are before you can start to say that I can ignore them. Here are some of the common mistakes. A common mistake is to simply, perhaps in your hometown there's a bank with a temperature sign and you simply pick off the value from the bank sign. Or you use a thermometer, but you just have the thermometer sitting in the sun, maybe on the hood of your car or inside the instrument case that's open and so forth. Both of those are inaccurate because with a thermometer, you need to measure the temperature of the air in the shade. That is the correct way to determine what the temperature is. Using the bank's temperature is almost always inaccurate because the temperature sensor is usually not exposed to free air and yet in shade. And so when I have done comparisons, I've rarely found the bank's temperature to be even within a couple of degrees of what the correct value is. The other problem that happens is for barometric pressure, surveyors either assume it's 29.9, which it probably isn't, or they listen to a weather forecast, or these days with smartphones get something off an internet connection that tells you what the barometric pressure is. First of all, you need to make sure that the barometric pressure is being measured very close to where you are. If you're even 25 or 50 miles away, it could be radically different. The other is that weather forecasts correct all the way down to sea level. So when they report what the barometric pressure is, it's as if they dug a hole all the way down to sea level and placed the barometer there. Now, they don't actually do that. They know exactly how much the elevation of a particular point affects the barometric pressure, or in other words, the weight of the column of air above the barometer, and they make that correction. And when you use barometric pressure for your measurements, you want to use the barometric pressure at ground level, not at sea level. And this can induce a huge error, and often is the bigger error of the two when it comes to applying corrections for parts per million. So the proper procedures is to have a thermometer on the site or near the site that's in the shade and has free air moving around it. I often tell people, with respect to the temperature, get used to estimating temperature, and if you can hit it plus or minus 10 degrees Fahrenheit, the error is only plus or minus 5 parts per million. And if you remember how this works, 5 parts per million converts to 1 part in 200,000, which is often much less of an issue than many of the other issues you might have in your survey that will cause the precision to drop way below that. When it comes to barometric pressure, you want to correct the forecast temperatures because you don't have a barometer, so you have to regard the fact that the weather forecast barometric pressure, weather forecast pressure, so I made a typo here, so I should say pressure, is corrected to sea level, and you have to correct to ground level. And there's different ways to do it. One way, if you're not too far up in elevation, is to say we will have a reduction in barometric pressure as we go up in elevation of 1.1 inches of mercury. Hg is the chemical chart symbol for mercury for every 1,000 feet of elevation change. And it turns out that this 1,000 feet of elevation change will have an approximate 10 ppm effect. So even at fairly low altitudes, and keeping in mind that some surveyors often use 29.9, even without paying attention to the weather forecast, that you can easily have 10, 20, 30 parts per million of barometric pressure error, and that can cause the accuracy of your survey to diminish quite significantly. Now, figuring out the error at ppm is sometimes a little tough for surveyors to do. And so I say use these rules of thumb. If the air is thicker, the light travels through the atmosphere slower. And when the light travels through the atmosphere slower, the indicated distance is longer, the measured value is longer. So the way to think about it is, let's say we have a time of flight EDM. So there's the EDM, there's the reflector, and of course the light goes out, bounces and comes back. And so if the EDM, if it's a time of flight EDM, it's measuring how long it takes the pulse to go out and come back. So can you see that if the air is thicker and the pulse takes longer to go out to the reflector and come back, it's as if the air was thinner at the normal density that's assumed in the EDM, that it's the same as if the pulse went out a longer distance. And then conversely, if the air is thinner, the light travels faster, and thus the indicated distance is shorter. So learn to think it through, and think it through correctly. And so just as an example, one of the things you need to figure out is what is the standard for your EDM. And there's different ways to do this. Sometimes your instruction manual will tell you. Sometimes there's a chart that plots temperature versus barometric pressure, and you can figure out where the 0 point on the chart is, and it'll tell you what it is. The most common is either 20 degrees Celsius, 25 degrees Celsius, or 0 degrees Celsius, not Fahrenheit. And the most common pressure will be 29.9 degrees, inches of mercury, which corresponds to 760 millimeters of mercury. So this is when ppm is 0. So let's say you are making a measurement at, let's say, 5 degrees or 15 degrees Celsius, and let's say that the pressure let's say that the pressure is 28.5 inches of mercury. What are these impacts on the distance measured? Because you can see that temperature going up and down will cause the air to be thinner if it's up and thicker if it's lower, because air compresses or becomes more dense when it's cold and expands or becomes less dense when it's warm. So in this case, let's say that the instrument was actually calibrated, or the standard is 20. So if the standard is 20 and we are measuring at 15, do you see that the air is colder and therefore the light is taking longer than for the true distance? And so we would have a negative correction of x ppm. The actual number x would have to be determined from either some equations or a table. And sometimes, as I said, these equations are pre-programmed into your EDM. But just for temperature alone, that would be the case. Now let's look at pressure. The pressure, standard pressure is 29.9, and that's what the standard is for this particular EDM. You are using it at 28.5. Now remember what pressure means, atmospheric pressure. When you have a barometer, what you're doing is measuring how heavy the air above the barometer is, and you do that by comparing it against a column of mercury. And a column of mercury that's almost 30 inches tall, 29.9 inches, exactly balances. They usually have a U-tube, sometimes it's referred to as a manometer, that tells you what the weight of the column of air is. So when the pressure is 29.9, the weight of the column of all this atmosphere above you equals the weight of 29.9 inches of mercury. So in this case, we're saying we have 28.5. To get 28.5, we need to have less air above us, meaning less pressure. If we have less pressure, it means the air is thinner. And so the light is going to travel through the air faster. And when it's faster, we have a distance that's measured. If you go back to my previous slide, when it's thinner, the indicated distance is shorter. So we need to add on this one, and so we would do a plus y ppm. Now the intention in this course is not to talk about how we calculate x and y, but for you to understand that the ppm is a combination of these two, and we can have situations where these two balance out. You notice one's a negative and one's a positive. They balance out and might actually mean very close to a 0 ppm correction. But you don't know unless you think it through, and that's the important thing. Because if you are measuring under conditions where they're both negative and both positive, you may want to be more careful about making sure that you have properly compensated for temperature and barometric pressure. Now, let's talk about something else, and that's what we refer to as the retroprism constant. So the retroprism constant is an interesting idea that you need to think about a little bit, and that's the fact that the density of glass is greater than the density of air. And if the glass, therefore, is thicker, the light actually slows down as it passes through the prism. Now, it turns out that the total distance traveled inside the prism is, let's call the height of this pyramid shape t. The total distance is 2t, which would put it right here. And so if we have a plumbing system, and let's just call it a plumb bob for now, the plumb bob would be right where the apex of that pyramid should be. However, light travels more slowly through the glass. And so just like we talked about with the air, it's another way of thinking about it is that the glass is very thick. The light is traveling slower, so it gives the impression that it's actually traveled out here somewhere. So having that problem means that instead of plumbing the prism exactly with the apex where the plumb line is over the point on the ground here, what we need to do is move the prism forward physically a certain distance equal to this error here caused by the fact that the glass is thicker than air. And that's where we come up with values like a minus 30 millimeter offset. We often talk about prism constants that are minus 30 millimeter. Now many surveys will just say this is a 30 millimeter prism, but they actually mean it's minus 30 millimeters. Why? Because what we're doing is we're taking the indicated distance, and by physically moving the prism forward, we're removing 30 millimeters out of the picture. Now it turns out 30 millimeters doesn't quite compensate. And so that's why we have electronic distance meters with different offsets. Sometimes it's based on the design of the prism or the design of what holds the prism. And we even have zero offset prisms. And in the case of a zero offset prism, what we're doing is moving the prism way the heck out so that all the error is essentially accomplished by physically moving the prism that far forward from the plumb line to which you're measuring. And this causes some problems, and we'll talk about this in kind of a general way here in a few slides. Now, let's talk a little bit about setting up of the EDM. But before I get into it, this is probably a good time to take a little break, end this lecture, and we'll pick up here for the next lecture and continue with this topic.